Hello, we are Group W2, and our project is a carbon fiber cryo tank.
To differentiate the project from previous years, we decided to make a pressure vessel for cryogenic applications. For this application, we'll need three layers: stainless steel, insulation, and carbon fiber epoxy. A stainless steel float ball is cut in half at the machine shop, which is going to be used as the end caps of the stainless steel layer. This is where we left off before the pandemic happened. We plan to have the end caps welded to a stainless steel tube, then add insulation, followed by the carbon fiber toe and epoxy wrap. After curing the vessel, we plan to do hydrostatic testing to test the vessel for any leaks. Due to the circumstances, the final project was changed to an ANSYS simulation. See the Gantt chart below for the project timeline.
The aerospace industry has shown an increase in space exploration over the last decade. This is due to the advancements in technology and further research. The main source of propellant for a spacecraft is liquid oxygen. We are designing a high-strength, lightweight, cylindrical pressure vessel for cryogenic applications while meeting ASME guidelines. Our pressure vessel will be able to maintain its structural properties at extremely low temperatures and withstand an internal pressure of 2 megapascals. The goal of this project is to assist the aerospace industry in designing a fuel tank for spacecraft applications at minimal costs.
Moving on to the tank's design, we have modified our design to be a two-layer design rather than a three-layer design for budget purposes alone. Money must be saved for welding and the valve. A formal production of the tank would have had that insulative foam layer, since it would have been absolutely necessary in the cold conditions of space, but we simply don't have the money or time. The design we were planning on making ourselves has two layers. The carbon fiber outer layer, which we would have wound by hand since we lacked the machinery required, and the steel inner layer, or liner, which would be made from a steel sphere cut in half, welded to a tube, with the perforated ring baffles welded on the inside.
Carbon fiber toe, epoxy, and a stainless steel liner tube are going to be used to make the carbon fiber composite pressure vessel. The toe would be wound around the stainless steel tube, which was going to be attached to a lathe. Testing and validation will be done through analysis of SolidWorks, and to measure the effect of cryogenic temperatures, a thermal stress load analysis will be used, and to measure failure pressure, a static load stress analysis will be used.
Initially, we used MATLAB code to determine the necessary radius to thickness ratio for our pressure vessel under ASME guidelines. After MATLAB was used, we then created a SolidWorks replica of the project to conduct simulations of the vessel under use. Once simulations were conducted and verified, we then researched and purchased the parts necessary to build our project. The stainless steel flow ball that was purchased was sent to the machine shop on campus to be cut in half, as they would be welded to the ends of a stainless steel tube, followed by the carbon fiber toe and epoxy layer wrapping.
Due to the pandemic, the group can no longer proceed with previous plans. These plans included welding and machining of the inner steel liner and wrapping the carbon fiber around it. The carbon fiber would then have been covered with epoxy and cured in an oven. This is not possible due to the closure of the university, which also means that the group cannot access the machine shop. Due to this, we had to reconsider and replan what steps had to be taken to move forward with our advisor's advice. The project will now be simulated in ANSYS with cryogenic conditions. The group will meet through online meetings using WebEx and similar software in order to complete the project to the best of our ability. We hope to reach a goal close as possible to our original plan, if not better.